Welcome to Wireless Future. I'm Emil Björnsson and I'm in a rainy Stockholm today, and in Linköping I have my colleague Erik Larsson. How are you?
Good, Emil. How are you this morning?
I'm great. So I was thinking, since we are at different locations, that we should talk about coverage today. So in particular coverage without beamforming. So I was planning to ask you some questions. So what does coverage mean to you?
So absolutely, coverage. Coverage in a way is being able to reach out, right, with wireless comms. And you can think of it like mathematically that, if you drop a pin at random on a map, what is the probability that you will have some pre-specified level of quality of service, say? More broadly, or colloquially speaking, I think coverage is all about making the customers happy for the operators, right? In fact, covering the cell edges is the difficult thing in wireless communications. If you stand and you gaze at the tower and you see it in close by or in line of sight, then coverage isn't a big deal. But if you're far away, or if you're behind some, you're in the basement of a house or something, you don't even have to be far away geographically, right? But that's when it becomes difficult. So coverage is the, ability of the system to reach out far away from the base stations or the access points, where far doesn't have to be, again, geographically. It could also be that someone is just behind some shadowing object or in the basement of a house or something. So that's really, I think, what we mean by coverage here. And
is this a concept that is applicable both in rural areas and in the cities then?
I think yes. In the sense that you'll have coverage problems both in rural areas and in cities, right? In the city, you will have coverage problems only when you are deep into the basement of a building or at some very difficult location, because typically you aren't very far away from the access point. So it's the free space path loss isn't that large, right? In rural areas, coverage problems mainly arise because you're far away in terms of distance. And really, to cover an area, either you have to spend a lot of power at your transmitter to reach out, or you have to focus that power spatially somehow, beamform it in the direction where you know that your users are located, right? So these are the only ways of really achieving coverage. But then maybe your question is also whether we speak of, because there are in wireless comms there are two limiting, there are several major and limiting impairments, but two impairments at least are thermal noise, to make the received power high enough in relation to the thermal noise, and the second is to make the received useful power high enough in relation to interference. And when we speak of coverage, then very often we really mean to win over the noise, right? In dense deployments in cities, like you said, there'll be a lot of interference that typically is the dominating limitation. But when we speak of coverage, very often we really mean how can we make sure that enough power reaches the receiver so that the received signal is high enough above the thermal noise floor.
So is coverage just one thing, or does it depend on what kind of application we are using? If we are making a phone call, or if we want to watch a video stream, is the coverage different, or how do we define the metric here?
Yeah, that's a great point. Obviously, we can define quantitative metrics. Like if we are using, say, a cell phone only to make phone calls, then it will be binary. Either the call goes through or it doesn't, right? But if you're streaming video, then it could be that, if you have very good coverage, you could get HD quality, say, or full HD or something else. If you have a little bit less good coverage, then you could still stream the video, but you would have to live with, VGA or some lower resolution. And if you have really poor coverage, then the streaming just doesn't work at all to any satisfactory extent. So certainly, more like theoretically or mathematically, you could think of coverage as a way of quantifying what is the probability that you can get a certain bit rate and so forth. But I'm sure if you were entering that very detailed discussion and game here, but certainly, you could define metrics like that, right?
Yeah, I know. I suppose that coverage really at least originally means the basic coverage in order to use the basic services. And then, the more we rely on data services, it also becomes more a progression between where you are in the cell, what kind of services you can actually appreciate.
Right. That I think is valid, and we can could take that as a basic definition of coverage. That it's like binary, right? Either the basic services work or they don't.
So you were mentioning that instead of just like sending out a lot of power, we could beamform the signals in a focused manner. So if we should beamform signals, I suppose we need to know where we should focus the signals, right?
Right, because beamforming, means shooting power into some specific direction in space, right? Or transmitting a signal in such a way that it reaches a focal point where Laura received power at some specific geographic location. And to do that, you'll need to know where to point this beam, obviously. And in general, in say communication theory, one speaks about transmission with and without channel state information. What that really means is that either the transmitter knows where is the receiver located so that it can form a beam specifically towards him, or the transmitter doesn't, right? So channel state information refers to the fact of the access points here, the base station transmitter, to know where is the receiver located.
So then we have two different categories then to talk about. So let's start with the case when you have channel state information. How do the beamforming work in that case? How do you obtain it?
Yeah, so if the transmitter or the base station here then has channel state information, that means that it knows where the receiver is located. And
geographically or in some other more abstract manner?
Yeah, it could be both. And to start with here, for the transmitter to be able to adapt where it is sending its or directing its power, it would have to have either a mechanically steerable antenna, think of like a parabolic dish that you could just mechanically steer, right? Like this, or it would have to use some sort of MIMO or phased array technology where you have multiple antenna elements, and each antenna element is connected to some circuitry that could change the phase and amplitude and so forth of the waveforms that are emitted. And now, if we are in propagation with mainly line of sight, then in principle you can describe the, say, location of a receiver by talking about the angle to it, the angle of departure from the access point, right? And that is typically the case at high carrier frequencies, like you operate at millimeter wave or higher. Then there's a lot of line of sight propagation there. Either we have line of sight propagation or the signal won't reach at all, right? So then we can just talk about like the angle. But at lower frequency bands, then, well, there might very well be line of sight, but very often there's a lot of scattering and even reflection going on in the environment, especially scattering, so that it doesn't always make good sense to talk about like a direction to the receiver, but it's rather that you want to make sure that each little antenna, if you have a MIMO array, for example, each little antenna knows is accurate enough. You have channel state information on like a per antenna basis at the access point, so that you know the channel impulse response from every little antenna in your MIMO array to the receiver, and therefore you can adapt the emitted waveform such that, well, each antenna emits a unique waveform, and these waveforms then combine in the air in such a way that you see constructive interference precisely where the receiver is located. So think of like these two regimes, right? With line of sight propagation, we can talk about angles. Non-line of sight propagation with a lot of scattering, then instead we have to talk about channel impulse responses per MIMO antenna at the access point and adapt the transmission based on that.
And current systems are supporting all of these things that you're describing, right?
Yes, of course. So now what I said here about like a MIMO array with many antennas, and each antenna measuring like an individual impulse response to the receiver, that's the main operational principle behind massive MIMO technology, which is the say, cornerstone physical layer in 5G, right? Yeah.
So what if we don't have channel state information at the transmitter then, or at the base station? What do we do then? We can still beamform, or?
Yeah, so here's the thing, right? If the access point doesn't have channel state information, so it doesn't know in a line of sight scenario, it doesn't know what direction the target or the receiver is located, and in the non-line of sight scenario, it doesn't know these impulse responses or anything. So, well, then you can't beamform, right? I mean, you could beamform like in some random direction or in some fixed predetermined direction, but you wouldn't know whether or not you'd hit your receiver, because you don't know where the receiver is located. So without channel state information at the transmitter, at the access point here, then you can't meaningfully beamform. So what do you do then in order to cover the cell? In order to reach these terminals, right? Well, one thing you could do is just use a single omnidirectional antenna, or something that radiates substantially, omnidirectionally, right? Or at least into like some area where you know that your receiver is located. It could be like a sector or something. Yeah. So that's one thing you can do. And if you have a MIMO array, there are also other things you could do. One thing is that you could sweep beams. So you could like shoot beams like this in different directions. If you think of like the angle, or think of a two-dimensional plane, and then you got like angles from -90 to +90 degrees, and you could like shoot beams in different angles, -90, -89, -87, and so forth, and hope that you'll hit the receiver at with some of these beams. And the third thing you can do is to use diversity transmission schemes, also known as space-time codes, that essentially generate waveforms that code across both space and time. So these are like the main options that you'd have if you don't have channel state information at your transmitter antennas.
Yeah, so we will talk more about the diversity schemes later. I came to think about maybe some analogy with big lamps, for example. If you want to light up a football field, you know where the players are supposed to be, so you can use a big lamp there to. But you can also have a flashlight with very narrow width of the light, and you save energy, I guess, and you sweep around in a way and look for objects somehow.
So you got to track the players, and
exactly. Or maybe on a stage, you either are lighting up the entire stage, or you are lighting up just where the actor is located. Okay, so a lot of people are talking about 6G now, and in particular, perhaps we have previous episodes about going up in the frequencies towards terahertz bands or things like that. So in general, then, is this coverage issues changing as we are changing the wavelength of the signals, or is it the same old physics all along?
Yeah, so the question really is, I think you meant whether it is more difficult or whether...
Yeah, is it more difficult? Do we need to use other methods?
Yeah, right. So is it more difficult to get coverage at higher frequencies? And the answer is partly yes. So here's what happens. When you go up in frequency, to shorter wavelengths, then, well, the path loss, at least for free space line of sight propagation, doesn't change. But what does change is the effective area of an antenna. So if you have a dipole antenna, then its effective area will shrink in proportion to the square of the wavelength, which is the reciprocal square of the carrier frequency. So, and that will directly affect your link budget. And the only way of making up for that loss is to use antennas with a larger aperture. And to increase the aperture of the antenna, then you could either build like a dish or something that is just physically larger, or you could build something like a phased array or a MIMO array that comprises of many small independent antenna elements that are electronically controlled or interconnected in some way. But now, once you increase the aperture of the antenna, you also increase its directivity, which means that, yes, we could recover this loss in the link budget that stems from the decrease in effective area of the antenna when we go up in carrier. But to make up for that loss, we would need to use antennas with directivity, which means also that we would need to know where to point these antennas, either physically or by controlling the small individual elements that they are made up of. So in that respect, getting coverage at higher frequencies is more difficult, yes.
Yeah, it's a very important thing that you're pointing out there, because you can often hear people say casually that if you go up in frequency, you get worse path loss. And then it's so important that the path loss formula always measures both the signal loss over there and the transmitter and receiver antenna. So it's very hard to couple this unless you do it in a way that you explained.
Yes, and it's an important misconception, I think. I mean, the thing is, the path loss does not change when we increase the carrier frequency, but the effective area of the antennas do. And that's why we get this loss in the link budget. And certainly, sometimes you also see like claims that, well, in fact, it isn't more difficult to establish coverage or reach far at high carrier frequencies. You just use an antenna with a larger aperture. Certainly that's true, but the catch is that to use an antenna with a larger aperture, you need to know more precisely where your receiver is located, and therefore orient your antenna either physically or have like some advanced, say, MIMO array or something, right? But if it's just one radiating like element, then you'd have to physically orient the antenna towards the target. So you need a lot of prior information on where your receiver is located. Anyways, yeah.
Yeah, maybe there's just one more detail around that even if the loss over there is the same irrespective of the carrier frequency, the interaction with different objects like penetration for buildings and things like that could still be different and make it worse at higher frequencies.
Certainly, that's a good point. I mean, we said the path loss doesn't bend carrier frequencies is only really not exactly true. I mean, there are, for example, there are some certain bands where rain in the air could interact with the waves and cause enormous drops. But in general, I mean, if you just think of free space line of sight propagation in vacuum, then there is no wavelength dependence. So that's the point, I think. Yeah.
So let's go back then to beamforming without channel state information again. So when I'm teaching MIMO theory, I like to talk about, there are 3 types of gains that you get from having antenna arrays. It's like beamforming gain, there's the multiplexing gain, and there's a diversity gain. So which one of these can you achieve without channel state information?
Yeah, so you certainly can't get the beamforming gain, right? Unless you have like an antenna that you orient physically, a high gain antenna that you orient physically that points into some specific direction. Or you have a phased array or MIMO array where you like configure it to beam into some specific direction. But then, of course, you don't know whether your receiver is located in that direction or not. That's the point, right? When you don't have channel state information. So really, you can't get useful beamforming gain if you don't know where the receiver is. And then you mentioned, I think the second was multiplexing. Multiplexing in MIMO all stems from the ability of the array to send multiple beams at the same time into different directions or focus power onto like different spots in space. And that you certainly cannot do if you don't have channel knowledge or channel state information. And the third you mentioned was, I think, diversity gains. So diversity gain refers to the fact that, well, if you have like an let's say array antenna with maybe 100 elements or something, and then you have a receiver somewhere with perhaps a single antenna, and you have independent fading across the array, then you'd have like 100 chances of getting the signal through, right? So that's known as diversity. And another name for that, by the way, is channel hardening, which I think is more common in the modern MIMO literature. And that you certainly can get without channel state information, without knowing where to point the beam. I mean, you can still use, as I mentioned earlier, this beam sweeping or diversity schemes or space-time codes to harness this diversity gain, the fact that independent fading across the array gives us many chances to get the information through.
So you mentioned that multiplexing gain is not something that we can achieve. Is this were you thinking particularly about like multiplexing of different users, or if we have a receiver with multiple antennas that have channel state information, can it decode multiple streams still?
You could. I mean, you could of course think of you could send multiple streams if the receiver had multiple antennas. That is certainly correct. I mean, you'd have a point-to-point MIMO channel then, essentially. Is that what you mean?
Yeah. Then I guess the difficulty will be to know how to encode it so that you can actually decode the signals. But
yes,
I suppose you can
in
use a bad precoder.
Yeah, you could, exactly. I mean, you could send multiple streams, but really to get any performance out of it, you would need this channel state information.
Yeah. So traditional base station before, maybe 4G or 5G, were this high gain kind of antennas that we might not call it beamforming, but they're still forming a very directive antenna beam towards, maybe it's going down towards the ground, not up into the air, and then it's supposed to fill a sector. And I think one of the engineering problems that you come across then is that you put it on a rooftop or in a mast, and you choose your tilting and horizontal and vertically, and is that a kind of like predefined beamforming where you can still try to tilt it so you get the best coverage?
Yeah, I think you could say that. I mean, so this becomes a little bit like a question of semantics, I think. What does beamforming mean, right? If you have like you have a high gain antenna, which is essentially what this is, right? Although it might be look like some kind of a grayish panel and composed of many small antenna elements that are interconnected with a microwave phase shifter networks and so forth, then certainly you could call that beamforming, I think. I mean, and you're right that traditionally then these are rather high gain, both in azimuth, but especially in elevation, and then it becomes important like how to tilt them and how to orient them and how to actually mount them physically on the tower. So certainly, but of course, again, the point is that, because these are high gain antennas, you will need to know exactly how to point them, right? Or you'll need some mechanism in order to adjust where they are pointing, depending on like traffic load or maybe other factors.
Yeah, I suppose if you are providing coverage of a certain number of kilometers in the countryside, you can try to tilt it in such a way that you're focusing your fixed beam towards the edge of the cell or something like that. Because that is maybe where you had the biggest coverage issues.
Right.
So now when we are talking a lot about beamforming without channel state information, I suppose many will wonder, what do we need this for? Is there anything in today's systems that is transmitted in this particular way?
I mean, so reach or transmitting information without channel state information would be either in order to reach users for which we haven't established yet a closed loop operation so that we know where they are and can be informed to them. I mean, it could be that you want to wake someone up, for example, a terminal, right, or a cell phone, or send a paging message, or which is like a message of the sort that please wake up and send something back so that we can locate you and figure out the channel knowledge or channel state information to you so that we can beamform. And so that's one thing. Another thing is that the systems also broadcast lots of information, like every tower, every access point broadcasts information on the sort that, look, here is tower number 5043. If you want to contact with me, please use the following procedure. And so that's known as system information. And then, I mean, more traditional is like, well, there might be a lot of things that are of interest to everyone, right? It could be even like a TV broadcast, for example. There's no point in beamforming it if you know that pretty much everyone will potentially be willing to receive it. But in modern, say, wireless standards, it's really the system information and paging or wake up messages that are sent this way.
So two terms that I sometimes come across when reading about beamforming without channel state information is open loop beamforming and slow fading. What are these terms meaning?
Yeah, so we got to be careful here that we don't conflate terminology, I think. But to start with this open, and so there's this term open loop beamforming and also closed loop beamforming, right? And that just means open loop means transmission without channel state information. So it's essentially just another word for that. Think of it like a control loop that isn't closed, right? So the controller has no idea really what to do, and then you just, if you don't have channel state information, you just transmit omnidirectionally all over the place. In contrast, closed loop operation, then we have channel state information so that we can form beams or focus power. So these are just two terms that are used more or less as equivalent to having versus not having channel state information. And what's the other term that you mentioned?
Slow fading.
Oh yeah, slow fading. So that one I think is slow fading. I think is one of the terms that's very often being misused, because when we teach wireless comms, right, and we talk about fading as a phenomenon, and fading is composed of two parts. There's the large scale fading, which includes like path loss and shadowing in a very typically slowly. And then there is the small scale fading, which is like Rayleigh fading and so forth. And I rather prefer to talk about large scale and small scale fading than slow or fast. Slow just refers to how fast does it vary, right? And that depends on like how fast is your terminal is moving and all that. Yeah, so maybe that's what you meant here.
Yeah, no, I think in some cases slow fading is also used as the scenario where you sort of transmit there you only see one channel realization and the receiver, I guess in textbooks it's sometimes used where the receiver knows a channel, the transmitter doesn't know the channel, but there's just one realization and you need to use outage measures in order to...
Oh yeah, I see what you're after here. So that's true. Sometimes we'll talk about fast and slow fading in let's say more information theoretic context or notion, where fast fading means that we have a code word and it sees many, or like an infinite number, but at least many different channel realizations, right? So there's a code that spans across many different channel realizations. We talk about slow fading, it's like, well, each code word sees only a single realization of the randomness in the channel. And so that certainly, and that's I think good and legitimate use of that terminology, certainly.
So is there anything in between the case with no CSI and perfect channel state information? Could we have some partial information or know something about a group of users, or are there some other cases?
Right, so certainly yes. I mean, for one thing, you might have like partial channel state information, which means you know something about the receiver, where they are. It could be like, I mean, in the most elementary form, it could be that you know that the receivers are in some kind of sector or some limited geographical area, right? And if you have that sort of information, then even a fixed high gain antenna, if you tilt it and point it appropriately, that would do good. That would like make the best use out of this limited channel state information that you have. So certainly you might know something, but not exactly the angles or directions and locations and so forth. And you could exploit that knowledge to do some kind of, maybe not exactly beamforming, but still some kind of partly directional transmission at least. And the other thing is that there are also situations where a single beam might be good for more than one receiver at a time, even for transmission of like dedicated information, right? And that's known as multicasting. So say, for example, that in a cell there are several users out there who are interested in receiving the same TV show or something that's going on in real time. So then, well, rather than just pretending we don't have channel state information at all and just broadcasting omnidirectionally, we could form a beam which is good for many users at the same time. And this is possible with, for example, this can be done with massive MIMO technology. And one trick that can be used here is to use a shared pilot, so that this becomes a bit technical now, but it's just like the transmitter array at the access point then obtains not channel state information to a single one of these receivers, but rather a linear combination of the channel impulse responses to all of them. And then when it later beamforms, it's like shooting multiple small beams at the same time, which then reach these receivers that are interested in receiving the very same data stream. So certainly this is a whole world of research and development, of course, to refine, the sort of protocols. But in general terms, exactly like you said, one could exploit also partial information about the channels.
Yeah, and I think you're also raising an important point there, that when people like you and me are talking about beamforming, we are not meaning that we necessarily send a focused angular beam like a flashlight in a particular direction, but more in a generalized form that we transmit with a certain directivity, meaning that, as you mentioned, we focus a signal at one location or at a multitude of locations, and we design the transmission so we get that focusing. We're not so much caring about how the signal look like close to the transmitter, whether it looks focused there, as long as it reaches the location where we want it to be. So in the beginning you talked about the beam sweeping, I guess, and also diversity schemes. I was thinking we could go in a little bit more detail on this. How are these related to each other? Is one better than the other?
Yeah, so let's see, let's recap. So beam sweeping meant that you shoot like a beam first at -90 and then at -89 and then -88 degrees and so forth, right? And diversity scheme, they're also called a space-time code, is more that you create some set of waveforms that are individual for each antenna, and you transmit these waveforms and hope that the effective radiation your transmission you get is omnidirectional, right? So in a way, it's like beam sweeping is a special case of space-time coding or of a diversity scheme. You can think of beam sweeping as a repetition code, more or less, that you send some piece of information in direction -90 degrees, and then you send the same piece of information in -89 degrees and so forth, and hope that, well, at least some of these beams are useful and will reach the receiver. So in that respect, diversity schemes and space-time codes are much more general and therefore better in general, right? There's one thing though here which is slightly more subtle and but still important, and that is that with a diversity scheme, it might be that the space-time code you send code over a substantial period of time, and then the receiver has to be awake over all that time and listen and integrate coherently. So integrate here means like collecting samples and combining them coherently in phase in some manner. Whereas with beam sweeping, it's really enough that at a very little instant in time where the beam hits the receiver, that it can listen during that very little instant in time and decode something. And then when the beams are sent in other directions, then that receiver isn't illuminated at all, and it doesn't matter whether it is asleep or whether it doesn't have to integrate samples, combine samples coherently or anything. So there are some advantages to beam sweeping over space-time coding, although fundamentally if we assume that the receivers are sufficiently capable, then space-time coding is always better than beam sweeping.
Okay, yeah, so it was clear to me what would be the potential benefit of the beam sweeping, but what was the benefit of the diversity schemes if you can be...
well, it's like with beam sweeping, it's like a repetition code. Whereas with a space-time block, with a space-time code, you can achieve a higher transmission rate. So think of it like it's like in isotropic fading indeed, then beam sweeping is equivalent to antenna hopping. Sending, you got two antennas, say, and what you could do is to either sweep a beam pointing like westwards and then a beam pointing like a bit of eastwards, and the same information in both beams. This is mathematically equivalent in isotropic fading to antenna hopping, using the first antenna first to send the packet and then turning it off and use the second antenna to send the packet. That's repetition coding. In contrast, with a space-time code, you can send two packets with twice the rate and still have them transmitted omnidirectionally. So in that respect, beam sweeping is just like a very restrictive or not so good, let's say, special case of diversity scheme.
I heard about something called the Alamuti code. Is that also a special case of space-time codes? Or?
Oh yeah. So that was the first space-time code that was invented, right? I think it was back in 1998. And it's a very clever scheme, where you use two antennas to transmit one symbol per channel use, and in a way that's omnidirectional, so you get second-order diversity if you receive with a single receiving antenna. And this invention by Sivas Alamutik, and I think it was end of the 90s, I think it was 98, spawned this whole field of research and development into space-time codes, and especially space-time block codes, so the Alamutis scheme is an instance of a space-time block code for two transmitter antennas.
And more generally, I suppose you have written a book on the space-time block codes, right? So, what does it contain? Is the sort of the theory still relevant today, or have everything moved on? There's a lot have been happening since you wrote it.
Oh yes, of course. This is, that's amazing. It's 20 years ago almost. But so yeah, we wrote this book, Space-Time Block Coding for wireless communications, and I was fortunate enough to enter this field at the right time and write, I think, if not the only, at least the first, say, a textbook style exposition on the topic, and it is certainly something which is highly useful. It's there. It's used in the standards. Now this becomes a little more detailed or technical, but within the world of space-time codes, there is a subclass of space-time block codes, which is what our book is about, and the special case of that is Alamutis scheme. And then that's for two transmit antennas. Then for general number of transmit antennas, there are non-orthogonal space-time block codes and orthogonal space-time block codes. Mm-hmm. And orthogonal space-time block codes have some very attractive properties. For example, they facilitate extremely simple decoding at the receivers and so forth. The problem is that beyond two transmit antennas, you have to compromise the transmission rate. So full rate orthogonal space-time block codes don't exist for more than two transmit antennas. So beyond what's in the book that we wrote, and in subsequent research where I more or less left the field after that, but others have continued, then lots of the research was focused on to finding orthogonal codes with a better rate than what was previously known. And I think it is probably fair to say that what remains from the field and which is truly most useful is some of these orthogonal codes, certainly, definitely the Alamutis scheme for two antennas, but also some non-orthogonal codes that have been developed later on and that have a lot higher decoding complexity than the orthogonal codes, but still manageable, right? So it's possible to win back some of this loss in transmission rate by spending more computational power on the decoding and So it was a highly vibrant field like 20 years ago, and but it did result in some things that are fundamentally extremely useful and are in the systems and standards that we are building today.
Yeah, I was thinking that during this almost 20 years, the capabilities of handsets must have been improved tremendously, so that some of these seemingly more complicated things might be easy to implement today.
Absolutely. Although it's also true that, I mean, you'll always push the boundaries, right, in terms of what you can build. And now there's this talking about Internet of Things and so forth, where you build potentially very simple devices that just can't afford to run complicated nonlinear decoding algorithms. And there's always going to be this trade-off. I mean, we built something that's very low power and very computationally efficient, and you still need schemes that can be decoded at low complexity.
So I suppose one of the requirements to use the space-time block code is that you have a transmitter with multiple antennas. And nowadays, when we have 32, 64 antenna massive MIMO arrays, are these space-time codes scalable in the sense that we can apply them in those cases? Has there been some evolution around that?
Yeah, I mean, they certainly scale, right? So there's not like a real issue around that. But what is a bit of an issue, though, is that for these diversity schemes of space-time codes and space-time block codes in particular to be useful, the receiver will have to estimate the downlink channel in order to detect the symbols or to decode. And that in turn will require downlink pilots. And that is an issue if you have a lot of antennas, because the amount of time frequency resources required for downlink pilot transmission scales in proportion to how many antennas you have at your access point, right? So there has been some developments in that field. In fact, one of my students the other year also did some papers and defended a dissertation on this topic. So there's been developments which are like tailored to how to make these diversity schemes and space-time block codes in particular adapted and useful for the massive MIMO setup, where we have like 100, maybe even hundreds of transmitter antennas, and therefore can't afford to send pilots in the downlink, right? I mean, and of course this issue with not being able to afford pilots in the downlink is a big deal, quite generally speaking, in MIMO, as we have talked many times. I mean, you and me, and also written a lot about, and it's one of the fundamental reasons for why TDD operation is superior to FDD operation, for example, in massive MIMO systems, right? But that is one thing here also that one has to consider when applying space-time codes in this context. Yeah.
So before we wrap up, I was going to ask you something about our wireless future. Looking ahead, that new technology components that people are doing research on now, we have had previous episodes on terahertz communications or on reconfigurable intelligent surfaces and things like this. So do you think a space-time block code will have a prominent role in any of these technologies? Or if someone wants to now go and read your book and figure out how to utilize this theory in the future, what would be the first places to look for open problems?
Yeah, good question. I mean, the short answer is yes, definitely. I mean, why? Because this issue of being able to meaningfully transmit when you don't have channel state information will always be there in any future wireless system. And as soon as we have like a transmitter which is capable of coherent transmission from multiple antennas, then, well, space-time codes are there as the basic enabling technology for achieving omnidirectional transmission with diversity and so forth. And I think that's probably also true in the context whenever, I mean, if you have reflecting surfaces in the environment, I'm sure there are many new things you can discover and optimize and so forth. And for terahertz, I'm not entirely sure what, I mean, as long as we have a coherent MIMO array, then the issues from a COM theoretic perspective aren't really very different from at lower frequencies. If you go
there's
up
more
high enough in
antennas
frequency,
potentially.
Yeah, maybe more antennas. So certainly there'll be like new issues, right? So I think the short answer is definitely yes. The long answer is that Certainly yes, but there'll be maybe new issues here to investigate and to discover, and something that we all should look carefully at, I think, when designing these future physical layer technologies. So.
Yeah, I suppose one of the new things that are really coming now is that we will have multiple antennas in the handsets as well. So maybe 4G terminals had like 2 antennas with different polarizations, but when we go for millimeter wave or beyond, we will have antenna arrays.
Yes, good point.
Are the spacetime codes usable in those situations as well?
They certainly are. But again, once we enter this regime of lots of antennas and potentially lots of antennas relative to the dimensionality of the channel coherence and so forth, there will be new issues to address, I think. So, still a ripe topic.
Yeah, great. So yet another episode where we are identifying new emerging or interesting research challenges in our wireless future. So do you have anything else you would like to mention on this topic?
Oh, not really. I think you really covered it all here, Emil. So thanks a lot for great conversation as always.
Yeah, and thank you to our listeners for once again staying with us and listen to our conversation. And as usual, if you have any particular questions about what we covered in this episode, please ask them, for example, on YouTube, and then we'll be happy to get suggestions on future topics or questions that we might talk about in some dedicated Q&A episodes as well.
Absolutely, and don't forget to like and subscribe us on YouTube and the other channels. So with that, I guess, thank you very much.
Bye-bye, and thank you.
Thank you, bye-bye.